Approximately 13.8 billion years ago, a singularity, an entity of infinite density and gravity, arose that quickly swelled and cooled, giving birth to our universe. This event is known to us as the Big Bang. However, speculation about such things does not provide answers, but only generates more and more questions. What was there before the Big Bang? Is there even a before in the universe, where time itself was born out of this primordial explosion? Are we the last chapter in an endless cycle of cosmic death and rebirth? The greatest minds of our species have proposed theories, each as mind-boggling as the next. Some speak of other universes, while others postulate a universe that breathes, collapses, and expands in an infinite cycle. Let's try to make sense of what actually happened before the beginning of time itself. Imagine a universe that breathes. It expands outward from one point, grows for billions of years, and then shrinks, drawing in all matter and energy. This is the essence of the oscillating universe theory. This model assumes that our universe is just one phase in an endless cycle of expansion and contraction, a cosmic dance that has neither beginning nor end. Each cycle begins with the Big Bang, an explosive moment of creation followed by a long period of expansion. Over billions of years, this expansion slows, stops, and then reverses. The universe begins to contract, which eventually leads to the Big Crunch. During the Big Bang, galaxies collide, stars are compressed, and all matter and energy is squeezed into a singular point of infinite density, very similar to the singularity from which the Big Bang occurred. But this is not the end, but the beginning of another cycle. The singularity explodes with another Big Bang, starting the next iteration of the universe. The lifetime of each universe in this model could be billions, even trillions of years, and each Big Bang prepares the ground for the next Big Bang. It's a fascinating concept, isn't it? Like a cosmic pendulum swinging back and forth between expansion and contraction, destroying and recreating universes in its path. However, the theory of an oscillating universe is not without flaws and criticisms. We've yet to understand many factors concerning the expansion of the universe, its exact energy composition, and how gravity behaves on such scales. And the data we've collected from the cosmic microwave background seems to point to an ever-accelerating expansion, not a possible future contraction. But as always, science continues to evolve, and once rejected theories might find new life in the light of new discoveries. Throughout our exploration of space and time, we've always thought of our universe as unique, a single bubble of reality floating in an endless sea of nothingness. But what if we are not alone? What if our universe is just one of an unimaginable multitude of other universes, each with its own laws of physics, its own history, its own beginning and end? This is the premise of the multiverse theory. Imagine a vast cosmic ocean in which countless bubbles appear and disappear. Each of these bubbles represents an independent universe, and our universe is just one of them among this cosmic foam. Some of these universes may be different from ours, have different physical constants, or even other dimensions. Others may be strikingly similar and may even contain life as we know it. What if some of these universes preceded ours? Could our Big Bang have been caused by an interaction with another universe? The multiverse concept challenges our understanding of our place in the cosmos. Nevertheless, it is a theory that remains highly speculative. While the multiverse theory is fascinating, it is also controversial. After all, if these other universes are beyond our reach, how can we detect or study them? And if the theory cannot be tested, can it be considered scientific? Nevertheless, multiverse theory continues to be the subject of research and debate among physicists. It represents the edge of our understanding, where science mixes with philosophy and observable facts give way to profound questions about the nature of reality itself. And yet, despite the supposed multiplicity of universes with all their variety of physical forces and dimensions, let us return to the realities of ours. Our understanding of the universe rests on two pillars of modern physics: quantum mechanics, which describes a world on the atomic and subatomic scale, and general relativity, which describes a world of very large dimensions. But what happens when these two worlds collide? According to Einstein's general theory of relativity, space and time are interwoven into four-dimensional fabrics known as space-time. Massive objects distort this fabric, creating what we perceive as gravity. On the other hand, quantum mechanics presents a world in which particles can exist in several states simultaneously, appear and disappear. It is a world that challenges our everyday logic. These two theories meet in the singularity of the Big Bang and in the heart of black holes, where the scales of quantum mechanics and gravity intersect. Scientists have long sought a theory of quantum gravity to reconcile these two conflicting views. One exciting idea that emerged from this search is the no-boundary proposal, championed by physicists Stephen Hawking and James Hartle. According to this theory, the universe did not emerge from a singularity. Instead, space and time are finite, but limitless, like the surface of the Earth. Just as you can travel the Earth without falling off the edge, you can travel the universe without colliding with a boundary. The universe would be a four-dimensional sphere, and the Big Bang would be a smooth point similar to Earth's North Pole, but not a singularity. In this model, asking what happened before the Big Bang becomes as meaningless as asking what is north of the North Pole. This is a pretty good way to get around the singularity problem at the beginning of the universe. Like the other theories we've discussed, the no-boundaries proposal is not without criticism and is still the subject of ongoing research. Nevertheless, it represents an intriguing attempt to bring together worlds incredibly large and incredibly small, pushing the boundaries of our understanding of the origin of the universe. Now let's look into the field of string theory, a theoretical framework in which the fundamental building blocks of the universe are not particles but one-dimensional entities called strings. Each string can vibrate at different frequencies, and these different vibrations produce different particles. Electrons, quarks, photons, all of them can be strings just singing on different notes. But string theory doesn't stop there. It also predicts the existence of more than 3 spatial dimensions with which we are familiar. These additional dimensions may be compacted or hidden from our perception, but nevertheless fundamentally affect the fabric of reality. In the context of our topic, one variant of the string theory, the pre-Big Bang scenario, or as it's also called, the ekpyrotic model, suggests that our universe may have been created by the catastrophic collision of 2 multiverse worlds or branes. What happens after such a collision? The 2 branes bounce off and apart only to come together gravitationally and collide again billions of years later, perhaps creating another universe. So what was there before the Big Bang? Well, in this model, it could have been another universe similar to ours, existing on a brane parallel to ours. And yet, string theory itself, although incredibly elegant and capable of combining quantum mechanics and gravity, has no empirical evidence. And as we already know, such things are very difficult to verify. But what if we choose a different approach? Instead of looking for a universe that preceded ours, what if we reconsider the very notion of nothingness? When we think of a vacuum, we often imagine absolute nothingness. But in the world of quantum mechanics, the vacuum is far from empty. This is a bubbling soup of particles and antiparticles that spontaneously arise and then destroy each other. This phenomenon is called vacuum fluctuations. The vacuum fluctuation model, also known as the quantum fluctuation model, suggests that our universe may have originated from one of these vacuum fluctuations. A tiny bubble of false vacuum could have inflated into the universe due to the principles of quantum mechanics. Such a bubble, due to phase transition or quantum tunneling, would begin to expand rapidly, and its edges would be pushed outward by negative pressure. Inside this bubble, false vacuum energy could be transformed into matter, giving rise to stars, galaxies, and eventually, you and I. So, what was there before the Big Bang? In the vacuum fluctuation model, it could have been a quantum vacuum, a sea of short-lived particles and antiparticles, and our universe was just one random bubble that managed to grow into something bigger. Now, while the vacuum fluctuation model is an exciting possibility, it also raises difficult questions. For example, why did this particular bubble expand while others did not? And how do we reconcile the idea of an eternal quantum vacuum with the apparent age of our universe? But as we delve deeper into the world of quantum physics, we find that it holds more intriguing possibilities. One of these possibilities is related to the field of research that combines quantum mechanics with cosmology. That brings us to the next model, the Big Bounce Theory. Imagine a universe that expands, contracts, then bounces back elastically. That's the basic idea of the Big Bounce Theory. Instead of a singularity in which all the laws of physics cease to exist, the Big Bounce Theory argues that our universe may have been born from the remnants of an earlier contracting universe. In this model, the universe is not compressed into singularity. Instead, because of quantum effects, it returns to a very small size and begins to expand again, leading to what we now call the Big Bang. This theory, like the oscillating universe theory, postulates a universe with no beginning and no end, but with an infinite cycle of expansion, contraction, and rebirth. In this way, it circumvents the singularities that plague the other models. However, unlike the oscillating universe theory, the Big Bounce focuses specifically on the transition point, the bounce between contraction and expansion. So how does quantum mechanics fit into this? Quantum effects are thought to play a significant role on the very small scales at which rebound can occur. According to quantum mechanics, particles can tunnel through barriers even if they have no classical energy to do so. Some theories suggest that the universe could use a similar quantum tunneling effect to bounce from a contracting state to an expanding one. Again, this theory is highly speculative and faces significant problems, both theoretical and observational. Can we find evidence for a previous phase of contraction in our present universe? Can we develop a quantum theory of gravity that can handle these extreme conditions? However, the Big Bounce theory is not without its flaws. The physics of what can make the shrinking universe come back to normal is still being investigated. Understanding how this process can occur without violating the known laws of physics is the main obstacle to this theory. The Big Bounce theory does not yet fit within our traditional notions of time and causality. However, as always in science, there are competing theories. For example, our universe could have been born from a cosmic object that we have already discovered but barely understand. Something mysterious, all-consuming, but perhaps also creative. A black hole? Black holes, mysterious giants of the universe, formed by the collapse of massive stars. They are regions of space where gravity is so strong that nothing, not even light, can leave it. The base of a black hole, according to the general theory of relativity, is a singularity, a point where density becomes infinite, and the curvature of space-time reaches an extreme degree. But what if these cosmic entities are not the end, but rather the beginning? Some physicists speculate that singularities inside black holes could give rise to new expanding universes. Thus, our universe could be the inner part of a black hole belonging to another parent universe. In this model, the Big Bang would correspond to the formation of a black hole singularity in the parent universe, and the expansion of our universe corresponds to the internal growth of the black hole. So, what was there before the Big Bang? It could be the inside of a black hole in another universe. And maybe every black hole in our universe can give birth to a new universe inside itself. Of course, this idea, like all those we've discussed, is a hypothesis and not without problems. How can we test this theory? Can we observe the effects of the parent universe? And how do we reconcile this with our current understanding of black holes and singularities? Loop quantum gravity, or LQG, is a theoretical framework aimed at reconciling the two giants of 20th century physics: quantum mechanics, which describes the very small, and general relativity, which describes the very large. Loop quantum gravity implies that space itself is not continuous, but consists of tiny, discrete loops. It consists of tiny, indivisible loops, just as a piece of fabric consists of interwoven threads. Applied to cosmology, loop quantum gravity, or more exactly, loop quantum cosmology, offers a rebound scenario similar to the Big Bounce, which we discussed earlier. In fact, loop quantum cosmology provides a specific quantum mechanical description of the universe's evolution, including the Big Bounce scenario. Instead of collapsing into a singularity as required by traditional Big Bang theory and general theory of relativity, the universe shrinks to a minimum size, but quantum gravitational effects become significant and counteract the contraction. Then the universe bounces back and begins to expand again. This means that our universe may have undergone a series of expansions and contractions, each of which began with a quantum jump. So, what was there before the Big Bang? From the point of view of loop quantum cosmology, it may be another phase of the universe, the contraction phase, which preceded the quantum jump. In loop quantum cosmology, the idea of a quantum bridge is truly fascinating. This bridge represents a transitional phase connecting our universe with its predecessor. Instead of singularity, the universe undergoes a quantum leap and starts expanding. This jump, this transformation from contraction to expansion, can be seen as a quantum bridge from the old universe to the new one. This quantum bridge is not a physical bridge in the conventional sense, but a phase of the evolution of the universe controlled by quantum gravity. So what is beyond the Big Bang? According to loop quantum cosmology, the previous universe is connected to ours by a quantum bridge. Although this theory eliminates the singularity at the Big Bang and offers an elegant quantum description of the evolution of the universe, it still faces considerable difficulties. Nevertheless, if it is correct, it offers us an amazing picture. A universe with no beginning and no end, experiencing infinite cycles of contraction, jumping, and expansion. Although these theories offer intriguing possibilities, for the most part they are still in the realm of speculation. Each has its strengths, its weaknesses, and none of them yet has conclusive experimental evidence in its favor. Even as we approach the answer to what was before the Big Bang, we should expect that each answer will open up even more questions. But the beauty of science lies in the process of exploration and discovery itself. Researchers around the world tirelessly study these theories and improve their models. And the study of even one theory goes a long way towards advancing the whole picture. So, what happened before the Big Bang? In a nutshell, at this point, we don't know for sure. But whatever the answer, the search itself enriches our understanding and inspires us to keep looking.